Go. Hello and welcome back on this wonderful Saturday afternoon to Calculus 2. We are going to talk about trigonometric substitution. We are going to use those trig integrals we studied the last time. Now the goal is to transform the function that will have a whole bunch of x's and roots and all that into a trigonometric integral and then solve it and then bring it back to x if you need to. Now, in order to learn this section, I'm going to teach a universal method that solves all of the cases, possibilities, right, rather than case by case. So, what we need to know, obviously, is going to be the right triangle with the angle theta, which has the adjacent to the angle, opposite to the angle, and the hypotenuse on the longest side. So now with that, you are going to have the 6 trigonometric functions you can write, but you technically just need 3. So sine theta is going to be opposite over hypotenuse. Cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. You do not need anything else, but you can. So what we are going to do here is realize, I'm going to call now these ones A, B, and C. Let me do that in red. So A, B, and C on the sides, and then we are going to write the Pythagorean identities. We have A squared plus B squared equal to C squared. We also have that C squared minus A squared is B squared, and C squared minus B squared is A squared. Now, what I'm actually interested in over here is that C is the square root of A squared plus B squared. So these are the ones that I actually care about. B is C squared minus A squared. And finally, A is C squared minus B squared. So I'm going to box these ones in blue and box these ones in blue. So if you know this much trig, you should be good to go for this section. Just to transform the problem, and then you have to use trig integrals from previous lecture to solve the problem. Okay, so I'm just going to jump into the book real quick and pull a whole bunch of problems. Please don't ask the puzzles. Thank you. All right, so as I said, in the book, it's going to be a little bit different in terms of the way they teach. I like to teach this method with this. So please use whatever you want. I don't care. Use whatever you want. It's just that, I happen to like this method because it's one fits all. Now, what is the trick here? Guys, look. Your problems are going to have a form of these roots. And hopefully you can notice that when there is a minus, when there is a minus under the root, your hypotenuse is always first. Do you see that? And then when there is a plus, both sides are legs. That is crucial for us to set up the triangle. So I'm just going to go to a random problem, and we're going to solve the random problem. the book literally gives you 100 problems to try. So it's awesome. So let's take a look at any random integral of square root of 9 minus x squared divided by x dx. So if this was backwards, right, you would be able to use basic u sub. If x was on top and root was on the bottom, right, all you need actually is just x on the top. If you put x on the top, it's a basic u sub, because you have x squared and then you have x for the du, right? So if this x was up, and doesn't matter where the root is, if x was up, you can do u sub, but it's not up, it's down. So nothing works. Your basic integral doesn't work, your u sub doesn't work, the by parts doesn't work. So nothing works, and we have to mess with this. So this is what we do. We set up our triangle with a theta, and now you need to distribute these values. Now, what did I say earlier? If there is a square root under, if there is a minus sign under the square root, the first value is the hypotenuse. So that's how I know that this is 3. Because this 9 is definitely that c squared, which is hypotenuse. So that's how I know that 3 goes on the hypotenuse. Because it's a minus, and whenever it's a minus, the c squared is the first, and that's the hypotenuse. And now, it doesn't matter where you're going to put x. You can put x here, or you can put x on the bottom. It doesn't matter. So let's put it there, which would make immediately this side to be 9 minus x squared if you do Pythagorean identity, right? That side would become 9 minus x squared. So this is how you set up the triangle. You need to know that if there is a plus under the root, then the 2 would be the legs. If there is a minus under the root, the first one is always hypotenuse, and the second one is whatever leg you pick, it doesn't matter. Now, the second part is to create 2 trigonometric functions, always using the side that has the number. So I'm going to have red and blue, because when you are creating trig functions, you always use pairs and a pair of sides. So you always pair with the number. And now the red one is opposite and a hypotenuse. Okay, so for the red, opposite and hypotenuse, that's sine, right? So sine theta is x over 3. From there you can solve for x, which is 3 sine theta, and immediately for dx, which is 3 cosine theta d theta, because we need to change everything into, right, we need to change dx as well. The blue one is going to be cosine of theta, which is the square root of 9 minus x squared divided by 3. And since you need to replace the square root of 9 minus x squared is 3 cosine theta. And you just replace things. You just drop them into the integral. The square root is replaced by 3 cosine theta. X on the bottom is replaced with 3 sine theta. The dx is replaced with the 3 cosine theta d theta. So let's do some color coding over here. I'm going to use the green one for x, which is connected with the green. I'm going to use the pink over here for the square root. And I'm going to use, let's say, orange to connect the dx with the dx thing. So you gotta use some chasing over here, but all of the pieces are there. Your 3 cosine theta is the square root, which is in blue. Your 3 sine theta is single x, which is there in red. And checked with the orange one is the dx substitution, which you get by differentiating x. So just a little bit chasing around to plug all of these things. The 3's will cancel. One of these 3's goes outside. So we have 3 integral of cosine squared theta over sine theta d theta. And now the question is, do you know how to integrate this, which is previous section. So, believe it or not, the lecture is over. That's it. That's the trig sub. You transforming the x's, right, into trigs, right? That's it. And the transformation happened through all of this mess. What takes over here is the previous section, right, when you just need to figure out how to integrate your trig function, right? So that has nothing to do with today's lecture. Obviously, we're going to solve all of the problems all the way, which is why you should invest about 90% of your effort practicing 8.4, because it practices both skills, and about 10% of your effort in 8.3 just to, get your feet wet. Because 8.3 is necessarily the part of this section to finish off every problem, right? The goal of trig substitution is to transform the problem into trig. Well, it's a trig integral at that point. So clearly, right, you will be using. So now we got to integrate this, this monster. And as you observe here, we cannot use u substitution because sine is in the wrong spot. So what I can do here, it's a little bit unconventional, but again, we are going to write the cosine as 1 minus sine squared x over sine x dx, and that will give us 3 integral of cosecant x minus sine x dx. And now cosecant is the evil one, right? So that's going to have that ln, oops, the negative ln. Of cosecant x plus cotangent x in absolute values, and then you have integral sine is positive, cosine, so it's going to be plus cosine x plus c. And unfortunately, the pain doesn't end here. Hold on. Do you see what I did? It's terrible. These are all thetas. They're all thetas because we have to go back to x. Holy nightmare. I know. I know. I would say it's my fault, but I don't want to. Because we are not done. This is not done. Now we have to go back to x. We have to go back to x. Forgot to close the parenthesis too. There we go. So now, negative 3 ln absolute value. And what's cosecant? It's adjacent or hypotenuse or something over something. What is it, cosecant? It's 1 over sine, which means? Beautiful. You will go to your triangle and read hypotenuse over opposite, which is 3 over x. And you'll just drop that there instead of cosecant, 3 over x. That's how easy it actually is. What's a cotangent?
Cosine over sine.
Well, in terms of sides.
Adjacent over opposite.
Beautiful. Just read it up there. Adjacent over opposite is the square root over x. So square root of 9 minus x squared over x. Beautiful. And then we have plus 3. What's cosine? Well, cosine was given to us. Square root over 3. And then we have plus c. And then these 3's will cancel. And we're done. Welcome to trigonometric substitution. Lock the doors. Problem number 2 coming up. Every problem is going to be the same. We don't care what functions we get.
So it just has to have something in one of those forms. A squared plus b squared square root, or
Yep.
c squared minus b squared, c squared minus a squared.
Yes. And if you look at the problems, they all have it. This is what the homework looks like in the book. And there's another page of this when you flip. Okay? So look at it. Can you find something squared minus plus something squared in every single problem, right?
What about for that one, like number 35?
Oh, there's always completing the square that you can do.
You just complete the square.
Oh, Jesus.
Don't worry about it. It's algebra, right? You can always do completing the square.
I'm terrible at that.
Well, that's what that's what all the extra time in the world is, you know.
You should be able to use Wolfram now.
You should be. I agree.
Thank you.
You have the support,
I appreciate it.
in your opinion. But the reality is that we all know that, right?
My opinion is the only one that matters. So.
I heard that so many times. So, as you can see here on this page, the homework in 8.4, the problems all look like this, and then even when it's hidden, right? A 3/2 over here, a half would be a square root, right? Now over here, in this problem, you have a square. Well, that's okay, because you can still put, it's like a square root to the 4th, right? So we can deal. We'll get there. So let's just pick another random problem and work on it. Well, let's pick, what should we do? How about 21, huh? Now, this is old edition of the book, so it's not going to match your problem, so that's why I'm not using the numbers. Dx over x squared, square root of x squared plus 9. What happened?
Oh, nothing. I was just so easily in the wrong projection.
Here's the projection. See how accommodating we are?
I know, I love it.
Don't get used to it, because you're going to transfer out.
Oh, one day. I don't know if it's ever going to happen, but hopefully.
So we have dx over x squared, square root of x squared plus 9. Same procedure, guys. Draw the triangle. Put the theta in. And say, I have a plus under the square root. If it's plus under the square root, then those two values are both legs, right? Now, you have option to write it as x and a 3 or 3 and an x. I don't care, right? Because legs are legs. Go either way. And then, using Pythagorean theorem, x squared plus 9 is going to go on the hypotenuse. We are going to use the red and blue, right, to put these pairs always using the number. One of the three sides will always be a number, and you will use that one twice. So for the red one, I can immediately see the tangent theta as x over 3. X is equal to 3 tangent theta, and then dx immediately is 3 secant squared theta d theta. As soon as you calculate x, you immediately find the dx, because you have to replace dx as well. All right? Don't discriminate. Be nice once in your life. So x equals 3 tangent theta, and then immediately differentiate to get the dx. Derivative of tangent is secant squared. Now go for the other one, the blue one. That's obviously going to be cosine. Cosine theta is going to be 3 divided by no coffin square root of x squared plus 9. And now when you solve for a square root of x squared plus 9, you are going to get 3 over cosine theta, and the square root is actually what? Very good. 3 secant theta. You have to obey the pairs. You cannot mix a tangent secant integral with a cosine. So your pairing is either sine cosine, like the previous problem, or this problem is going to be secant tangent. Now remember how I told you put this 3 and x any way you want? If you had them backwards, it would be cosecant cotangent pair. Same calculation. It's just you have to chase minus signs. So if you don't want to work with cotangent and cosecant, all you need to do is to swap the legs. That's all it takes. All right, let's do some chasing. Guys, I would ask you to look rather than write, because you can write later. I'm going to explain. Well, actually, you can watch this later too. Do whatever you want. Integral. Dx on the top, marked with orange, is the dx, which means 3 secant squared theta d theta. Divided by, I have x squared. Therefore, I'm going to square the x, square the 3, square the tangent. I'm going to label that green over here. And that is going to be my 9 tangent squared theta. That's my green. And finally, I have the square root, and that square root is just going to be my 3 secant theta, which is this pink highlighter. So I have 1, 2, 3 units. Dx is a unit. 1, 2, 3 units there. You see that you had to fix that x squared because you had x. It was x squared, so you had to square everywhere to make sure that that fits there. And then you have your square root that's replaced by, this is just like blocks. You take a full block and you just replace it. And now cancel everything you can. So we have 1, 9 kicked outside because these 3 will cancel the other 3. You see that one of the secants cancels, and you have tangent squared theta, and then d theta, and from this point on, good luck. Because now it's 8.3. So one more time, this transformation here, what you see is your 8.4 trigonometric substitution when you replace all of the x's with trigonometric functions using the triangle and those systems. So now, blank slate. It is time for us to do a trig integral. It has nothing to do with what we did before. we're just going to solve this one as a completely new problem. So what now? Well, we have a secant tangent pair, and the question is can we work this somehow out? And the answer is no, because you need a secant squared, right, to make u equals tangent. You don't have that. You need another tangent on top to make a secant tangent for the bank, but you will need a secant, which you don't have. So it seems that none of the stuff works. What now? Well, there is always a trick of trying to actually transform the problems in sines and cosines. Maybe that would help. Perfect. So let's see if we can use sines and cosines. Secant is 1 over cosine theta divided by sine squared theta over cosine squared theta d theta. When you do the double fraction, cosine squared will multiply 1, go on top, and then you will have sine squared theta cosine theta d theta. And now you see that one of these cosines die, right? And you have 1 over 9 integral of cosine theta divided by sine squared theta d theta. And this is great because u equals sine, right? U equals sine, and you have a cosine on top for du. So u equal sine theta, du equals cosine theta d theta, and that's going to give us 1 over 9 u to the minus 2 du, which is going to be 1 over 9 u to the minus 1 over negative 1 plus c, and that is going to give us negative 1 over 9 u, which is sine theta, plus c. Are we done?
No.
Why not?
We have to go back to x.
There we go. So you need to read the sign. What's the sign from the picture?
Sine is going to be x over 3.
That's the tangent.
X over square root.
X over square root. Beautiful. So negative 1 over 9 times x over the square root of 9 plus x squared. And then deal with the double fraction. That's going to be negative square root of 9 plus x squared divided by 9x plus c. Is this correct? Yeah, it looked good, you know. It's like, whatever, who cares, right? But let's say you care. What could we do to check it? Yes. Differentiate. If you get the original problem, this one, you win. Otherwise, it's wrong. You gotta do it again. So now what I'm going to do to check this is I'm going to simply take the derivative of this, which is going to be riddled with chain rules and quotient rule and all of that good stuff. And hopefully it simplifies into an original problem and we can move on to another example. So let's see the derivative. So we are going to use the chain rule over here. Quotient rule. Quotient rule is the main rule. So quotient rule. We have 9x squared in denominator. On the top, we put 9x first, and then we need to take the derivative of negative the square root. The derivative of this is going to be, so first we're going to have 2 square root of 9 plus x squared, and then the derivative of this on top of the inside, which is 2x, so negative 2x. Where is the negative? So I have to drag that negative as well. Minus, copy the top, which is negative square root of 9 plus x squared times the derivative of the bottom, which is 9. And then plus 0, derivative of c. So now what do I have? I have, when I deal with the x's and so on, I have what? 2 and 2 will cancel, so I have to worry about that. And I have negative 18, no negative, negative 9 x squared, negative 9 x squared divided by the square root of 9 plus x squared minus plus 9 times the square root of 9 plus x squared, everything divided by, I'm just going to put 81x squared because I can. So now I'm going to multiply top and bottom by the square root of 9 plus x squared to kill the double fraction. And when I do that, in the first one it will just cancel it, so I just get negative 9x squared. On the second one it will be plus 9, and then this will be 9 plus x squared, because square root times square root, it gets right cancelled. And then over here I have 81x squared times the square root. I like that because I did have the square root in the denominator before. So now I have negative 9x squared on top, plus 81, and then plus 9x squared, haha, there it is, divided by 81x squared, square root of 9 plus x squared. I was worried for about 17 seconds, and now we see that 81 and 81 will cancel for us to get exactly what we need, which is 1 over x squared, square root of 9 plus x squared. Now I gotta flip like 5 pages to find the original problem, but but there was the answer. Yes, got it, right? So awesome. Well, next example. We're not gonna dwell too long.
I was going to cherish the victory for a minute.
No.
It's too long.
Too long. Oh my god.
Just pain. So how about I give you guys to enjoy a problem, and then how about we let's do the weird one, and you can play with this at home. So x cubed divided by 81 minus x squared, everything squared, dx. Right. So here is a problem, and generally students recognize the trig sub as soon as you have addition or subtraction of perfect squares, which would make perfect sense, obviously. And we do see 81 minus x squared. Now, don't be discouraged if you see, 6 minus x squared, because 6 can be just root 6. You're just dragging out root 6 everywhere. So it's not required to have 81 or 36 or 100, right? You can have any number, because you can just use root of it, right, to do the math. We draw the triangle with a theta, and we have a subtraction now. If we have subtraction, what is the rule?
Hypotenuse and a leg.
Hypotenuse and a leg. And the first one is always hypotenuse, so 9 goes right there. Now put the leg, let's say x goes there, and if we end up with a, let's say, secant, cosecant pair, if we don't like it, we can just put the x there and just change it. Right, so we are aiming for sine cosine pair or secant tangent pair, just because we don't want to deal with the negative signs on the, right, that's the only reason. It's not like we hate them or something, but it's just extra negatives, extra opportunities for mistakes. So we don't like them. And over here, we're going to have a square root of 81 minus x squared. I mean, that's a Pythagorean theorem. I understand we don't have a square root in a problem, but we'll have to fix it with exponents and stuff. Red, circle towards the number. Blue, circle, function, and a number. So when you are creating trig functions, you always have to use the one with the number. And in this case, it's 9, which is hypotenuse. So the red one is going to be sine of theta, which is going to be x over 9, from where x is 9 sine theta, and dx is 9 cosine theta d theta. You have to get dx immediately. As soon as you see x, boom, dx, next step. Blue, cosine theta is going to be square root divided by 9, from where the square root of 81 minus x squared is going to be 9 cosine theta. Now, do I have x in the original problem? No, I have x cubed. That means that I have to fix this to x cubed by placing cube on everything. Do I have a square root in a problem? No, I have it squared, which means I have to put the fourth power everywhere to make up, right? The 2 out of 4 will kill the root, and the other 2 will be the square that you need for the problem. So substitution here is not as easy and straightforward as in previous problems, right? Because you have to fix these exponents, but it's still doable. Rewind the video if you have to watch it again. I have a 9 cubed sine cubed theta divided by 9 to the 4th cosine to the 4th theta, and for my dx I have a single 9 cosine theta d theta. Observe that all of the 9s cancel because you have 4 on the top and on the bottom, and one of the cosines cancels. So technically what I have is tangent cubed theta d theta. Do we all agree? Tangent cubed theta d theta? And if I have tangent cubed theta d theta, the only method that I can solve that tangent cubed is by separating one out and then transforming to secants and all of that good stuff. So we're going to peel off one tangent. We are going to convert this tangent into lies. Secant squared theta minus 1 times tangent theta d theta. And then that splits into 2 separate integrals. The first integral is tangent theta secant squared theta d theta minus the integral of tangent theta d theta. We have our u sub now for the first integral, where u is equal to tangent theta du equals to secant squared theta d theta. So the first integral is nice and simple, u du. Awesome. The second integral is also u sub, but in a different way, because this is integral of sine theta over cosine theta. That's how you integrate tangent. So now your u sub, the orange u sub over here, is u equal cosine theta, and then du is negative sine theta d theta. So now the second integral, I can't use u, I gotta use g. Because the integral over here, when I write it, is going to be dg over g, and see, that one is in terms of u, so you have to bring in the blue stuff, and if I have the u for the other one, it will be confusing. The first integral is 1/2 u squared minus the second integral is ln of g plus c, and now we bring back our trig, so this is tangent squared theta minus the ln of absolute of, and the cosine, right, is goes in here, plus c. We are not done, because we have to go back to x. So time to read the tangent of the picture, and tangent is x over the square root. So 1/2 x over square root of 81 minus x squared, and all of that needs to be squared because it was tangent squared, minus ln absolute. Cosine needs to be read now, and the cosine, I think we had cosine, yeah, it's the square root over 9. Bueno. Square root of 81 minus x squared over 9 plus c. Now you can apply a square on the left, which will kill the root. So you actually have x squared divided by 2 times 81 minus x squared. So the square killed the root, minus the ln of square root of 81 minus x squared divided by 9 plus c. Now, before we end the class, I just need to make sure that if you are using technology to check these answers, this answer might look different in the computer solution because they might not have this 9 at all. The answer would look the same, and just there will be no 9, and you will be going crazy. Where the hell did the 9 go? If you use the log identities, ln of a over b is ln of a minus ln of b. That would make ln of square root of 81 minus x squared over 9 as ln of square root of 81 minus x squared minus ln of 9. And this thing here is a number which gets absorbed by plus c. Gets absorbed by plus c, and that's why it would just plain disappear from the computer answer. So the tech answer might be x squared over 2, 81 minus x squared minus ln of the square root of 81 minus x squared plus c, not having that 9 at all. And the only reason is because, right, the ln 9 is a constant, gets absorbed by plus c. Actually, in this case, would be a plus because, right, the minus in front of ln would distribute. But there's just a little, little warning for you if you try to do these problems at home, and it's just, is there the next level from here? Of course, just put the limits on the integral, like 3 to 7, and then make sure you compute those, right? So there are ways to make this worse, always ways to make this worse, right? But I hope that the method that I'm showing in terms of just one triangle, one method, right? So it's either a minus or a plus under the square root, and always making sure that you are creating your trig functions towards the number, right? So number has to be the part of whatever you're writing. I separate it always in a blue and the red because, you know, color coding is easier to see with the picture where it came from. And then obviously the easiest part, right, is to bring back everything to x at the end, because you have the triangle and you just, whatever trig function you have, whatever you guys have, you will just read it off of the picture. I am sad that we did not hit any of the problems that actually have inverse trig functions show up in the answer. Well, actually, I can force one real quick. It will take two. Well, we have time. Lock the doors. Let me force one. Remember how you had to memorize the formula for inverse tangent? Perfect. So
I don't remember it now.
yeah. So you had to memorize that the integral of 1 over 1 plus x squared dx is equal to the tangent inverse of x plus c. And then we also talked about if you have 1 over a squared plus x squared dx was 1 over a tangent inverse of x over a plus c. So these are the formulas that you had to memorize in Calc 1. And then I believe we had a little discussion in class regarding this x over a and all of that business. So that's exactly what I want to do now. Just 1 over, let's go with 16 plus x squared dx. You know the answer. It's 1/4 inverse tangent of x over 4 plus c, right? Just a is 4. Stuff it in, you're done, right? But then you are tutoring someone and they say, why? Say no more. Here we go. Time to show off your mad skills. Theta. I don't have a square root. That doesn't bother us. We'll put x and a 4 and the square root of x squared plus 16, right? Does not bother us that there is no square root. We'll fix it later. So what do? Well, I create my trig functions towards the number. So I have my red and my blue. The red one is going to be the tangent, obviously. So we have tangent opposite over adjacent, which is x over 4. So your x is equal to 4 tangent theta, and dx immediately 4 secant squared theta d theta. The derivative of tangent is secant squared. Blue pair is cosine. It's going to work out to be secant, but we start with a cosine. Cosine is 4 divided by the square root, x squared plus 16. The square root, I'm just going to abbreviate. Square root is now going to be 4 over cosine theta. And finally, square root of x squared plus 16 is going to be 4 secant theta. And now when you want to plug everything in, you have 1 divided by, and this is where you see, oh, no square roots. Great. Square everywhere to kill the root. So now it's just x plus 16. So you are getting your 16 secant squared theta. And your dx is 4 secant squared theta d theta. Secant squared dies with secant squared. 4 and 16 die to 1/4. and you are just integrating d theta. What's the integral of d theta? Very good. Plus c. And guys, we're done. Then you go, I don't have a trig function in the answer. So how do I go back to x? Well, you can use any of the 6 trig functions because they all have thetas in them. Just need to use inverse. So to convert theta to x, use any trig function. Now we already have that the tangent theta is x over 4. That means that theta is equal to the inverse tangent of x over 4. So plug that in and we get 1/4 tangent inverse of x over 4 plus c, as we have foreseen with our formula. How cool is this? And now you have a week to enjoy this and practice. So we just showed the formula. Instead of memorizing the formula, we just did the trig sub and we got it.
Are the other ones going to start popping up more too, or just tangent?
That's it. You have sine, cosine, tangent, secant. That's it. You will pick up the patterns. What happens when there is a plus? What happens when there is a minus? You will pick up that pattern because that's the way the book teaches it. They say, if you have x squared minus a number, use substitution, blah, blah, blah. If you have x squared plus a squared, use substitution, blah, blah, blah. And then you have to memorize 3 cases and 3 substitutions. And you can. I'm not insulting anyone's intelligence. You know where the hell breaks loose? When you are to go back from thetas to x's. You have no triangle in front of you. So now what? Right? And you have the inverse. You have a sine function, but your substitution was tangent. Right? So now it's inverse sine of tangent, and you have to crank the extra calculations and so on. It makes it so much worse. Right? When you start the problem with the triangle, you have the triangle, and then you develop your problem. You are in charge. You are in control of the problem all the time if you do it that way. I don't know why they don't teach it. Even the Larson book is not teaching this method. No one is. I don't know why. I don't know why.
How else do you want to do it? Just memorize everything?
Yeah, that's what they have in the book.
There's not enough brain capacity. That, like, it, oh no.
This is the Nick version.
No, I actually figured it out when I was a student. Because I don't like memorizing. So I figured this out when I was taking this. Because I said, how hard can it be? You just have a triangle, right? It doesn't matter which way you flip, right? The triangle. And the only thing that took me some time was to figure out that you have to write your functions towards the number, right? When you are in a triangle. So your side, whatever side has a number on it, is the one that has to be included. As soon as I figured it out, the rest was a joke. But I haven't seen this taught in any of the textbooks. And I've seen Rogowski, I've seen Larson, I've seen Thomas, I've seen Stewart, I've seen our book, Briggs, right? None of them. They all have, these are the 3 cases, these are the 3 possibilities, plug it in, all the, One method solves all of them. That's it, done. Bye.